Hello. In this video, we will go over the research that goes on in Dr. Ellen Wan's research lab here at the College of Engineering at the University of Missouri. Dr. Wan's research is focused on producing high-value bioproducts from renewable resources. Biomass is a renewable organic material mainly found in plants. It is widely available as a feedstock for biofuels and bioproducts. Our lab uses different kinds of biomass feedstocks such as switchgrass, softwood, and hardwood for value-add applications. In this video, we will show you how we make graphene-based sound sensors from lignin, a major compound existing in biomass. This is done using a direct laser writing technique. Carbon dioxide lasers are frequently used in machine shop and industrial applications for cutting and welding, while lower power level lasers are used for engraving. Interestingly, this direct laser writing technique uses CO2 lasers to induce a 3D porous graphene-like material, also called laser-induced graphene, or LIG, from various carbon-containing substrates. When applying a certain laser power, localized high temperature and pressure generated by the laser beam can result in a carbon arrangement towards fewer layers of graphene along the 3D porous structure in the substrate. Laser-induced graphene has many good properties, like high conductivity, good thermal stability, and high catalytic activity. These features make itself a versatile platform for nanomaterial applications with high performance, such as physical and chemical sensors, supercapacitors, and electrocatalysts. In order to apply lasers onto lignin, a lignin-based film must be fabricated. This is done using additives such as nanocellulose, starch, and polyvinyl alcohol as a binder. Here, we are showing an example on how to make lignin-based film. First, make lignin dissolved in a solution, like an alkaline solution, and then cast the mixture onto a petri dish. The mixture will now be air-dried. Next, the film is peeled off from the petri dish and cut into a desired dimension for direct laser writing. In this step, different patterns can be designed depending on application. Also, different laser parameters can be adjusted to tune the properties of the laser-induced graphene. Here, we used a Mizzou Tiger logo as our pattern. So the blackened area with the tiger logo was observed upon laser irradiation. Such area is also where graphene was formed, being embedded onto the surface of the film. Here's the end result. Laser-induced graphene can be used in the film directly or transferred to a new substrate, depending on the application. Here, we are transferring laser-induced graphene to an elastometric substrate called dragon skin. This is a biocompatible silicon-based material used to fabricate flexible and wearable physiological sensors. First, the liquid state dragon skin was uniformly spread on the blackened area on the film via spin coating. After curing, the graphene will be firmly attached onto the solidified dragon skin. The final step is peeling off or water lifting to remove the film residue. Finally, we obtained a transferred LIG onto the dragon skin. A state-of-the-art sound sensor is fabricated and attached to the throat to detect voice. By connecting the sensor to a computer, we're able to collect different signals when saying different words. Laser-induced graphene is a piezoresistive material. This means that the material changes its resistance when it is compressed or strained. In our body test, the sensor will be attached to the tester's throat. When the tester says a word or a sentence, the muscles around the throat area will move and apply strains to the sensor. Saying different words will cause different movements, so the LIG will have corresponding resistance changes. The signal can be detected and recorded by an instrument. Here, we present the resistance signal of the sensor when the tester says, "today." beautiful, and today's beautiful. No matter what the tester says word by word or together in a sentence, the signals of words today and beautiful are consistent and repeatable, which indicates that the sound sensor has excellent performance in detecting minor muscle movements. Not only is our lab investigating the sound sensor, but we're also engaged in developing Ligninbased supercapacitors and heaters from biomass. We believe these biomass-based graphene materials still have more to be explored. We hope you enjoyed this presentation of the research that goes on in our lab. Thank you for listening.